Hello students. Last time we discussed on how to build a decision tree for the minimization of a sum of squared errors. Today we are going to focus on the topology of the tree, all right? And we are also going to, in addition to look at the topology of the tree, we are going to also discuss a few concepts related to the classification tree. Right, we discussed mainly the regression tree, but we will also introduce a few concepts related to the classification tree. Let's go to the tree topology of the tree. Now, what happened is that normally you would have a tree that is going to be grown fully, all right, a tree which is going to be grown fully uh, using the different criteria, using the criteria that I explained to you last in the first video. Okay, there will be a tree that will be grown of a certain size. We will define the tree T note as a large tree. And what is going to happen is that by going through the different procedure that I explained to you last time, the tree will continue to grow up to a certain point. Up to a certain point, it will grow until a certain point. What point? It depends on a stopping criteria that you decide to have for the tree to grow. For example, you may decide the tree to stop growing when it has reached a certain minimum node size of, let's say, 5. When we talk about node size, I'm not referring to the number of terminal nodes, but I'm referring to the number of observations. Number of observations in a node. All right, how many observations you've got in a node. And of course, the smaller this node size, the bigger the tree is supposed to be. All right. Now, one of the problems that you have when a tree is grown to a maximum size is that normally this tree will perform very poorly on an independent data set. So it will perform very well on the training set, but unfortunately it will perform very badly on the testing set. We don't want such kind of trees. We want our performance to be good in the testing set. Okay, this is one of our priorities when we are building a decision tree. Why is it so? Because the decision tree is a learning algorithm. You are going to learn the characteristics of the data and come up with predictions. Of course, when you learn the characteristics of the training set, you learn it very well. Very well means you have a very big tree with so many split variables and split points. You come up to a situation where you have learned the tree, the tree, you have learned the training set well. Then what is going to happen is that the performance on the training set will be very good. That is, the error rate on the training set will be low. But that same tree, when you apply it on an independent set, the test set, you can't expect the same thing because the characteristic of the independent set is different. So then the decision tree will perform poorly. So what do we want then? We want a tree that is not too big. We don't want a too big tree. We want a tree that has been that will perform well on the testing set as well. And how do we do that? This is by the concept of pruning. We are going to prune the tree in our in your day in whichever example you are applying. We are going to prune the tree. Pruning means you are going to cut down different branches into it. For example, we may decide to say we are going to cut down these branches. In the end, we come up with a decision tree with fewer branches. The concept of pruning is about cutting down branches from your tree. You are going to cut down many internal nodes to leave you with fewer terminal nodes in the end. And By doing so, your tree size decreases. And how are you going to do this pruning? It's by a concept that we call cost complexity pruning. We are going to apply the cost complexity pruning to be able to prune a decision tree. In other words, you have to decide, you have to understand that when you prune a tree, how far would you prune that tree? If a tree has been fully built with, let's suppose, you have 30 terminal nodes, all right, how far shall you prune that tree? Shall you prune that tree up to the point of getting 10 terminal nodes, or shall you prune that tree up to the point of getting 5 terminal nodes? This is the question that you need to ask yourself. To what degree shall I prune that tree? And this is what I explained through the cost complexity pruning. Okay, we will get to understand a kind of balance that we will go through to decide on to which level we want that tree to be pruned. So let's move to the cost complexity pruning now. When you are pruning a tree, a large tree, which is what we define as T note in the earlier slide, when we are pruning a tree, we will come up with a subtree, all right, and a subtree that we will call as T, for example. And what is going to happen when you put modulus here? This stands for the number of terminal nodes that you have in a certain tree. The number of terminal nodes that you will have when you see this, these two bars here, which represent the modulus here, what it means that we are referring to the number of terminal nodes that we have for the tree. The number of terminal nodes that we will have for the fully grown tree, which is defined as T node, the large tree, will obviously be greater than the number of terminal nodes that we will have for a subtree T. All right, it's going to be greater than the number of terminal nodes that we will have for the subtree T, which means that when you are pruning a tree, you will move from T node to T, where T represents a smaller tree with fewer number of terminal nodes, obviously. And these definitions are what we already discussed last time. I'm not going to go through the same thing, but just bear in mind that when you see this modulus, we are referring to the number of terminal nodes. Make the difference between what we discussed there. The node size has nothing to do with the number of terminal nodes, although they are going to be related in the end. But the node size refers to the number of observation in a terminal node, okay? In a terminal node, or not necessarily in a terminal node, in a node simply, all right? In a node. It represents the number of observations that you have in a node. But whereas here we are not referring to the number of observations, but we are referring to the number of terminal nodes. And this is one of the ways that we will use to identify the size of a tree, for example. Okay, we can identify the size of a tree through the number of terminal nodes. Now, to illustrate the concept of cost complexity pruning, we will, which is also known as the weakest link pruning, by the way. Weakest link pruning. Another name for the cost complexity pruning is the weakest link pruning. To illustrate that, we will come up with certain notations, and then from these notations, you will understand what the cost complexity pruning is about. So here we go. The idea here is that you want to minimize this. This means what? It's about the training error. It's as simple as that. It's about the training error. But we want to minimize this training error, obviously. And to get to that, we will need to go through these different notations first, which are not very difficult to understand. Let's go through it. Remember that we are working in the regression setting for the time being, because the criteria that you are going to use to prune will be different, obviously, for the case of a classification tree. Now, the NM that you see here represent the number of observations that you have within a certain region. What do I mean by this? Let me just give you an example to illustrate this idea. You remember that here there was, for example, the number of years less than 4.5, and you had three different regions. For years less than 4.5, you had one region. For years greater than 4.5, you had two different regions with respect to the number of hits. Now, let's suppose I'm talking about one particular region here, region 1, R1. Let's call this R1, okay? You would understand that in your data set normally, in your data set, you would have a full data set with years, and this represent the log salary. Why represent log salary? You will have years, you will have hits, you will have so many variables. But if you are considering this region R1 basically means what? You go in your data set and you identify for any value that goes less than 4.5. For example, the years at Major League, let's suppose you've got some, if the first baseball player spent 3 years in Major League, another one spent 2 years, someone else 5, someone else 6, someone else 1, 2, and things like that. So what is the number of equation? Let me do a last one, and let's suppose you've got 4 here, something like that. What happened here is that when you are referring to region R1, you are referring to the number of observations related to that region. Related to that region means what? It means for all years less than 4.5. This is 1, 2, 3, 4, and 5. There are 5 observations which are related to region 1. So the N1 and M, region 1, is in our example 1, 2, 3, 4, and 5. So that's what it would have been if we take this example to illustrate this principle. Okay, so here we go. This is what it means. And then remember that you have been fitting a constant C cap M. C cap M is obtained by taking the average within that particular region that we just said by summing yi over the average of the output within that particular region. That is, sum your output divided by the total number of observations. Let's get back to the example to illustrate that. So just like you have years, you would have a log salary for each and every player, all right, within the data set. You would have 5.0, let's suppose 4.5, you have something like 7.1, 4.5, things like that, okay? So what is the idea of the CCAP1? CCAP1 is what? CCAP1 is what? CCAP1 is simply the average of all the values within the region concerned. Remember that the region concerned relates to these observations. Relates to these 5 observations. So if the region concerned relate to these 5 observations, I will have to do an average of these different sets of values. This is what is going to give me my CCAP1, and I'm going to get the average here. This is my CCAP1 that I was referring to, okay? So we understand these two things now. One is the number of observations within a particular region, M. In the example I took was region 1, for example. And then you can compute the CCAP. But then there is something that comes in now. You have a kind of impurity measure that comes in. QMT relates to what we call the impurity measure. Okay, QMT is what we refer to as an impurity measure. Okay, And what is it about this impurity measure? It's something very straightforward in the context of a regression setting. The idea is to compare your actual value of y with what you have fitted, that is your constant, your mean, right? If all the values of y are equal to the mean, that would mean that this sum would be equal to 0. All right. In other words, that would have been the purest node that you can imagine of. But we all understand that generally this is not going to happen because you will not have fixed values everywhere in a data set. Within a certain variable, you won't get a constant value everywhere because there are variation. There will always be a number here in there. All right, but the smaller the number, the better it is because the impurity measure is going to be smaller. So what I want to just point your attention to here is that you will have, based on the y that this refer to y, but you will have your constant c cap that you are going to fit. When you have done the average of these four values, you will have your c cap here. All right, C cap 1 that you're going to compute. The C cap 1 will be a fixed value, all right, when you do the average of 5 plus 4.5 plus 2 plus 3.2 plus 4.5 divided by 5, you will get a certain value, let's suppose A, all right? So what you have to do then, it's a fixed value that you're going to get. The difference to the square of these will be computed. The difference of these to the squared will be computed. And when the difference of these are computed to the squared, what is going to happen is that you will be able to get your first Q1T. That is, you will have your first impurity measure for a certain node, which means that here you will have an impurity measure that you can compute for that node. You can also compute another impurity measure for that particular node, another impurity measure for that node. That is, for each terminal node, you can compute an impurity measure, because here for Q1T refers to only that particular region that I was discussing to you earlier. Then you have other regions which you have to consider, and you will have the different impurity measures that you will compute. Okay, so this is what QMT refers to, the impurity measure. The smaller it is, of course, the better it is. So let's get there. Having illustrated and understood these different terms, what they mean, we can come back to here. All right. So what does all this represent? So C alpha T would basically refers to your training error, because you have to understand something. If you look at this for the time being, just look at this, just forget that for a moment. If you just look at that, you would understand that this is showing us the sum of squared errors for each node, all together added, right? So you have here, when you look at this, it refers to, you have N1 Q1T plus N2 Q2T up to the total number of nodes that you have, all right? The total number of nodes that you have, Q plus N modulus T Q2 modulus T, all right? Sorry for the space, I don't get it here, but N modulus T, so it continues like this, okay? Qt, excuse me. Here we go. So what is happening here is that you are going to take, this is not Q2, excuse me here, it is Q modulus T. So what you are going to do here is that if modulus T represent the total number of nodes for a particular tree, let's suppose you have 30, then you would have to add all the 30 sum of squared errors, of course, multiplied by the number of observations that you have. So basically, it's just giving us this for each observation, but a bigger sum is applied again to this, in such a way that you are not referring to only one particular node, but you are summing all the nodes together. So let me get back to this tree here. It's like as if what I'm doing here is I'm finding an overall measure of accuracy for the training set using all the different impurity measures together. Okay, that's what I'm doing. Don't forget we are multiplying by the number of observations here. So this is the principle behind. We are doing an overall measure here. This is this part. This is this part. But of course, you will see that this does not end there. All right. In a general setting, you would stop here just to evaluate how good your model is or not. But here, what we are doing is that we are adding something to this, another component to that. We're adding an additional component to that sum of squared errors. All right. We are adding another component there. And in this component, you will see that there is a certain value alpha. All right. You will see that there is a certain value alpha multiplied by the total number of terminal nodes within tree T. All right, the total number of terminal nodes within tree T. And what is this alpha? The alpha is what we refer to as the tuning parameter. The tuning parameter, also known as the cost complexity parameter. All right. And what does alpha do? Alpha, what it does is that it controls, alpha is a tuning parameter, rather, which controls the trade-off between the subtree complexity and its fit to the training set. The subtree complexity, the subtree T complexity, and its training, um, and the trade-off between the subtree complexity and its fit to the training set, to the training data. So it does that by evaluating the error that you have here. Of course, if you think about it well, the smaller the value of alpha, what happens? If alpha is 0, the subtree T will just, the subtree T that you have here, this tree would just, this T would be just equal to T, would just be referred to T node. All right, it will be the largest grown tree. If alpha is equal to 0, you are just getting your fully built tree. There is no difference about it. You are just getting a normal sum of squared errors without this component. So in other words, it's just this modulus T has nothing to do with a subtree. It's basically the fully grown tree that you have grown, that you have built. But here, when is what happened is that when alpha start to increase, this is where things get interesting. So let me just remind you, when alpha is equal to 0, the subtree T that we are referring to will simply be equal to T node, that is the biggest tree that you have. Why? Not why, but rather don't forget that this would turn out to be 0, and you are going to get the training error directly as it is through this C alpha T. But when alpha is increasing, all right, when alpha starts to increase, there is a price to pay for having a tree with many terminal nodes. Listen to me well. When alpha starts to increase now, if it is not equal to 0, when it increases, what you are doing is that it says that this error that you would have obtained originally will not be as it was, but it will increase as well. Because obviously, if alpha is increasing, the error is increasing as well. So there is as I said to you here, when alpha increases, you have a price to pay for the tree with the maximum number of terminal nodes. So what do we want? We want this alpha to be a certain value where the tree will not be too big or too small as well. If alpha is 0, you have a fully built tree, that is the largest tree. But as your alpha increases, branches start to be pruned from the tree. Why? Because try to understand this properly. If alpha equal to 0, you get a fully built tree. But when alpha increases, you have to understand that the number of terminal nodes that you would have in the tree cannot be as it was originally. If you had 30 terminal nodes in the fully built tree, now you cannot have this. Because if you keep this fully built tree as it is, the number of terminal nodes, your error will increase because you are adding an alpha multiplied by this number of terminal nodes. So your error will not be this anymore. Your error will increase. What does this mean? If you want your error to be still relatively small, you need to decrease the number of terminal nodes so that your error overall in the end does not get to increase, but still it decreases or stays nearly the same as it would have been earlier. But at least the idea is that it does not increase. So then it means that if you are increasing your alpha, obviously you have to decrease the number of terminal nodes in your tree. And by decreasing the number of terminal nodes in your tree, you try to keep a balance here. You try to keep a balance, here, right? You try to keep a balance within this total error rate, the training error. So this is the idea. As alpha is increasing, the number of terminal nodes should decrease. And in other words, what you are doing here is that uh, you are pruning. You are pruning your tree. So just to repeat, as alpha increases, the number of terminal nodes need to be decreased to reduce the cost complexity. All right, as alpha is increasing, the number of terminal nodes has to decrease to reduce the cost complexity. And as we increase alpha, branches are being pruned from the tree. In other words, you will not have 30 terminal nodes, but this will decrease now probably to 10 or depending on the value of alpha that you are using. So that's a little bit the idea behind this formula here. It's a bit similar to what you studied in the context of lasso regression. The higher the value of alpha, then beta shrinks more up to the point of getting to 0 in the lasso regression. So the higher the value of lambda, the fewer variables you were left with, all right, because many variables would have been shrinked to 0. And it's a bit the similar kind of concept here, okay, if you want to look at it like this. It's a bit similar kind of concept. So here we already discussed a little bit about this. I'm going to skip this part. You can read through it afterward. And what we are going to do next is that we are going to apply whatever concepts we have done. We're not going to do it in this lecture itself, but we are going to do it in the class next time. We are going to learn how these different concepts apply in practice using the iter's data. All right, using the iter's data, we are going to learn all these different concepts. So we are going to learn how to build a decision tree and how to prune a decision tree using cost complexity parameter, using the cost complexity pruning. All right, and this would be applied in the context of a regression for the time being. But but we will not end there. Rather, we are going to continue now. This we will do it in class next week. We'll do it in the Zoom lecture next week. But for today, we are going to continue with the classification setting. You remember that the QMT that we referred to here was the impurity measure that we were referring to, was based on the minimization of a sum of squared errors because your y was quantitative. But when your y is categorical, things changes a little bit. The principles are the same, all right, in building the tree, but only a few things changes, all right. The splitting criteria changes a little bit. First of all, as I told you, now we are going to work in the classification setting. When you refer to the classification setting, we are not talking about, for example, predicting log salary, but we are, for example, talking about classifying individuals according to their credit risk. Let's suppose credit risk would be either good or bad. If it is good or bad, you have two classes here. All right, the classes, that is your classification outcomes, take two possible values, 1 and 2. All right, so within this setting, k is equal to 1 or k is equal to 2. K is equal to 1 refers to good, k is equal to 2 refers to bad. So we are going to take this example of credit risk to illustrate some of these different concepts that comes in. Remember that the difference applies in the criteria for splitting the nodes and also for pruning the tree. Otherwise, everything stays basically the same in terms of principle. Here we go. Remember, the impurity measure that you used in the regression setting was based on the minimization of sum of squares. But the impurity measure that we are going to use in the classification setting will be a little bit different. In fact, we will consider three different impurity measures. But to be able to understand these three different impurity measures, you have to understand what this is about first. This is important because we are going to use that terminology in the different impurity measures that we are going to see. Okay, let us talk a little bit about what this is about. Uh, in fact, this is just a proportion, okay? But a proportion which has been determined for a certain class key within a certain region M, all right? And there is still this concept of indicator function that comes in here. Maybe to illustrate this, I'll take an example for you to understand. Suppose I have a data set where yi represent the credit risk. And you've got to make things simple, we'll take it as only one variable, all right? We've got one variable. Suppose, first of all, let's put it there. This represents your credit risk. But suppose you have income as one of your variable, x1, okay? And you will have different sets of values for income in terms of thousands. Suppose the income is in terms of 1,000 rupees. You have 10. So these are the different values of income that you have. And then you have a credit risk which comes in, all right? The credit risk will be classified as good or bad. Okay, so suppose you got something like this. Bad, good, bad, good, bad, good, and something similar to that. So what is happening here? You have your actual values in your data set. You have 7 individuals, I suppose. And then you have your different incomes. Now, what happened is, let's suppose I build a decision tree starting with the variable income is less than 10. Let's suppose it is less than or equal to 10 rather. I'm not going to take the less than or less than, but I'm going to consider it as less than or equal to make things easier because it was we would have an issue because we would have only one observation. So let's suppose I take it to be less than, no, not less than 10, excuse me, but I will take it to be less than 15. Yes, less than or equal to 15 as my first region, less than or equal to 15. Oh, excuse me, I'll take it 20. All right. Suppose I define a region as x1 is less than or equal to 20. And all values that are less than or equal to 20 refers to one region R1. Okay, to one region R1 for a certain variable x1, which is going to be income, let's suppose. Okay, but there are other variables that comes in, but we are taking only one to illustrate the idea. So what is region R1? For less than or equal to 20, region R1 relates to these. 1, these are the 5 values that relate to region R1, that is for, as you would see here, for xi, belonging to region R1. Xi in our first example here would be belonging for our observations xi to belong to a certain region R1. So x1, x2, x3, x6, x7 here belong to region R1 based on this decision that I've decided, based on this split point and split variable that I've decided. Okay. Then what is pickup mk that we have defined? Pickup mk is what? First of all, m in our example is 1, pickup 1, and k depends on what you are referring to as k. Let's suppose I said k equal to 1 represent good, and or let's suppose k equal to 1 represent bad, and k equal to 2 represent good. K equal to 1 represent bad, and k equal to 2 represent good. So if I say pick up 1, 1, all right, we get back to this formula. Pick up 1, the region 1, and class 1, that is bad, is equal to this. That is, you take the sum of the indicator function that you have here. What does this indicator function does? It basically return 1 for all values of y equal to k. Otherwise, it returns 0. So if I'm referring to k is equal to 1, okay, so my indicator function, if you see it there, my indicator function, suppose I put a high here, my indicator function here would return 1 for k equal to 1 and 0 for k is equal to something else. Like here, k is equal to 1. This observation, it returns 1. Here, k is not equal to 1. It returns 0. K is not equal to 1. K is equal to 1, excuse me. It returns 1. We don't care about this because it's not part of our region, Rm. But here, k is not equal to 1. So we return 0. But k is equal to 1 is bad, so return 1. So what do? We sum according to the principle here. We are going to sum these different values. So 1 plus 0 plus 1 plus 0 plus 1, which gives us 3. All right. So which gives us 3. This is 3. And then multiplied by 1 upon nm, and m is the number of observations within that particular region m. Okay, so the number of observations that you have within that particular region is 1, 2, 3, 4, and 5. So 3 out of 5. This is pickup 1, 1. Pickup 1, 1 is just the proportion which relates to the class proportion of that class, proportion of observations within that of that class within that region. Proportion of observations of that class within that region. All right, so pick up 1, 2 now. I think it's quite obvious it's going to be 2 out of 5. But if you look at it in terms of the indicator function, it will be like this. Now, if k is equal to 2, you return 1, otherwise return 0. K is equal to 2. Here it's not the case, so it's 0. Here it is. Remember, k is equal to 2 represent good. K is equal to 2. Yes, you return 1. K is equal to 2. No, you return 0. So what is it? You count how many you've got. 0 plus 1 plus 0 plus 1 plus 0, which is 2. Out of total number of observations that you have within that region is 5. I think it was obvious anyway. You could have already just taken 1 minus 3 out of 5. Okay, but this is just for the illustration purpose of this formula, what it means. So that's a little bit what the proportion is. To sum up, the proportion here relates to the proportion of a certain class within a particular region. But then there is something else that comes in now. Km is the argument that maximizes pickup mk with respect to k, right? And what is this? It means that, let's have a look at this. If we take that particular example here itself, if we take that particular example, it says that we have a class Km, that is K1 for that region 1 that we were discussing here. All right, we have a class Km which is represented by the argument that maximizes this proportion with respect to k within that region, obviously. Within that region, it stays the same here, 1, 1. So what is the proportion that maximizes, what is the highest proportion rather, right? This is like saying what is the highest proportion, which is the maximum one with respect to k. So the maximum proportion that you have between these two sets of values for that particular region 1 is obviously 3 out of 5. So if it is 3 out of 5, what is the value, what is the k that is used to maximize this pickup mk? The k is 1. So what you understand from that, it means that k1 is equal to 1 in this particular example. If this was the highest proportion, k1 would have been equal to 2. But in our example, the one that is highest is k is for a class k equal to 1, that is class k equal to bad. So if we have to predict, what does this mean? It means that if you were to predict or to classify records for people who are having a income less than 20,000, we should classify them according to 1. 1 means bad. This is what it is telling us. It is telling us that k1 equal to 1 for that particular region means, in other words, we are classifying all the records as 1. So if we try to understand this here, it means that k1 is classifying all these records that are less than 20 as 1, means bad. So all the records that are less than 20,000 are these, less than or equal to 20,000 are these. So what our algorithm is telling us, we have to classify all these as bad. And I think you would understand there that the next step would be to compare what we have predicted with what we have actually. All right. And the closer they are, the more they are similar, the better it is. All right. But the worse, the further they are different, the more they are different, the worse it is. All right. And you would already observe here that there is misclassification, for example. For the first one, there is no problem. It predicted it correctly. But for the second one, you see that there is a misclassification already. For the third observation, it's okay. But for the fourth, you see that there is a misclassification. For the fifth, there is no problem. You already saw that there are 2 misclassifications out of 5. All right. So this is where I come up now to how you measure the impurity. Just like in the regression setting, you add y and you add y cap. Sorry, you add y cap, which was defined as c cap rather. Okay, C cap is our y cap in the regression setting. You were comparing them by mean squared error, but now we are going to compare these two things differently, not through mean squared error, obviously. Okay, there are 3 different measures that we are going to see. Let's have a look. We start by the simplest one, which is the misclassification error. Okay, and then I will just discuss briefly the difference between these different measures. Okay, although they are relatively similar in some ways, but they are nevertheless obviously different. I'm going to discuss that later on, but let's take a look at these formula. All right, let's take a look at this one first, and then we can have a look at this, which are basically the same thing. This one tells you what you need to look at your observation yi, that is the true values of yi in your data set, if they are not equal to the argument that maximizes k, the argument k that maximizes p cap mk. If they are not equal, what we are going to do is that we will return 1. Otherwise, we will return 0. Within, of course, a particular region. Do not forget, we are not talking about the whole data set. And then you will divide by the number of observations within that region. So let's have a look at the example. If we want to evaluate the misclassification error rate, you have your y, you have your predicted values of y that you have done. That is, you have your km that you have here. If yi is not equal to km, you return 1. If they are equal, do not return 1. And then you add. Let's have a look. Is yi equal to, let's take this out of the formula for a moment. So is yi equal to k1? K1 is defined as beta as we just explained earlier. So is it equal here? It's equal. So return 0. It will return 1 only if they are not equal. Are they equal? No, they are not equal. Are these two equal? They are equal, so it's supposed to return 0. Do not forget the formula which says that if they are not equal, return 1. Here, they are not equal, return 1. They are equal, return 0. So what does the formula says? Add all of these values, that is 2, out of total number of observations within that region. You have 5 observations within that region, so it is 2 out of 5. This is our misclassification error rate. The smaller it is, the better it is. Another way of looking at it is through that proportion, obviously, which is same thing normally. What does it mean? It means that I need to take 1 minus the proportion within the data that relates within the region M, obviously, within the data within region M, that relates to class Km. All right, the proportion that relates to class Km. So let's get back to the data. Here in this data, forget this for a moment, all right, but just have a look at this one. In this data, within class A1, how many were Km? What is the proportion of K1 that you have? K1 was equal to 1, that is bad. How many bad you've got within the data? You have to take 1, subtract the proportion of bad. Okay, that's what it says. 1, subtract the proportion of bad, because Km relates to bad. I'm not talking about good here, I'm talking about bad. So what is the proportion? 1 minus the proportion of bad. You have 1, 2, and 3. So you have 3 out of 5, which is again 2 out of 5 as we have just calculated earlier. So it's like just counting 1 minus the proportion of bad. You get the wrong and the wrong classification. If this were B, If this was B, the proportion would have been 1 minus 0, which would have been perfect. Okay, but this is not the case here. So this is what the misclassification is about. And as you would note, the misclassification error rate is relatively intuitive and simple for implementation. But nevertheless, it has a disadvantage, is that it is not a differentiable function. What do I mean by differentiable function? I will just show you I'll show you a graph in a moment of these three different measures, how they look like, and you would understand what I mean by that. Okay. So in general, as I said to you, it's relatively simple to interpret and understand. But there are other measures which are more amenable to numerical optimizations, all right? And these are the Genie Index and the Deviance, also referred to as the cross entropy, all right? Um, they also have their disadvantage, by the way, all right? These two methods, they have a disadvantage is that they are more sensitive to changes in the node probabilities compared to the misclassification error rate. Why am I saying so? You will see within the graph that I'm going to draw how this is about, what this is about. Okay. Now, in a general setting, what you need to understand though is that we usually apply the misclassification error rate in softwares and so on. Okay, although we software also provide for Genie Index and Deviance, but um, to guide the cost complexity, any of the three measures can be used. As I said to you, any three of these three measures can be used, cost complexity pruning, but still we will generally use the misclassification error rate. But deviance is also easy to understand, in fact. Okay, now if, by the way, when you see k dash, it means not k, all right? If k, for example, was equal to 1, k dash relates to not k. Not k means it could be 2, 3, 4, 5, 6, depends on how many classes you have, okay? But for the example that I was referring to, good or bad credit risk, k dash would be equal to 2 simply, all right? So what the principle is saying is that you need to sum p cap mk multiplied by p cap mk dash. So it's like saying let's suppose we are talking region 1, p cap 1, 1 times p cap 1, 2. All right, that is the idea behind. Now, what you need to understand is when you refer to a node, let's suppose you have said income is less than 20,000 and you are classifying all income is less than or equal to 20,000. I'm not using the notation that we are used to less than, but I'm referring to less than or equal to here to be consistent with the example that I took. And you classified all the records as bad. In the previous example, you saw that when you have classified all the records as bad, in reality, not all the records were bad. Okay, but let's assume all the records were bad as such. If all the records were bad, excuse me, if all the records were bad, what would have happened is that pcap mk would have been equal to 1. And then pcap m1 2, that is for region 1, there would have been no bad at all, would have been 0. So in other words, you will get 0 as a value. So this value of 0 means that you have the purest node ever here, the purest node, that is for all income. But this you get and when it is equal to 0, this means that it is the purest node ever. But normally things are not always like that. Okay, you see, you won't have any difficulty in classifying such record if all the records are consistently bad. It means that it is the purest node ever. But in the previous example that we took here, you saw already that it would not be equal to 0. okay? Because if you take 3 out of 5 multiplied by 2 out of 5, you will not get equal to 0. So, but still, in this example, we have been able to classify either as good or bad because they are not equal. Let's suppose we had 4 observations. Let's suppose we had 4 observations in all within that region, and you were having 2 as good and 2 as bad. That would have been a problem because then it would mean that if you multiply these two together, you would get 0.5, 0.25, excuse me, 0.5 multiplied by 0.5, which is 0.25. And 0.25 as an impurity measure would mean that it would be hard to classify such record. You understand? Because you don't know whether it should be good or bad. It's equally likely to be good or equally likely to be bad. But in our example, we still had the opportunity of classifying records as um, uh, as bad here. Okay, so the principle states that you need to take, in our example, 3 out of 5 multiplied by 2 out of 5. Right, but the closer the value is to 0.5, obviously, the closer it is to 0.5, the more impure the node is. The closer it is to 0, the less, the more pure it is, or the closer it is to 1 as well, the purer the node is. All right, the closer it is to 0.25, all right, the closer it is to 0.25, the more impure the node is, as you could have seen earlier, because such state means that it is hard for us to classify a particular record. Okay, but the closer it is to 0 or 1, if it is 0, it would mean that it is a pure node. You won't get 1 because if you take 1 multiplied by 0, you get 0. But if it is close to 1, let's suppose 0.99, it's still a very good thing. All right. So it means that it's easy for us to do the classification without any problem. So we have a pure node. So that's the principle of Genie Index. It's a bit the similar kind of thing here, but the only difference is that now we are not working with the values as they are, but we are working with pickup mk multiplied by log of pickup mk. All right, and because log of pickup mk will generally yield the log of a proportion will generally yield a negative value. That's why you have a negative value that you will see in the formula. So the principle is basically the same. It's just mathematically different for mathematical reasons, obviously. Okay, and coming back to these mathematical reasons, let me just remind you something, that these two functions here would are generally functions that can be differentiated. All right, the Gini index and the cross entropy are differentiable, which means that they are more amenable to numerical optimization. But this is not the case for the misclassification error rate, because what you would understand is that when you will plot the misclassification error rate, you will see that the distribution looks something like this, which means that when you have something like that here, it's hard for numerical it's not very easy for manipulation mathematically. Okay, these ones are more or less easier for manipulation mathematically. So let's try to see the difference between these different error rates in terms of a graph and to understand better. Okay, we are going to do that in R. We are going to have a look at when the proportion is a certain value. When the proportion is a certain value, pick up here starting from 0 to 1 on the x-axis range, what is happening to 1 minus pickup mk1? What is happening to pickup mkm? You will see that, for example, in the context of pickup mkn, it will increase up to a point here. And for the others, you will see that it's going to be something like this. All right, it's going to be differentiable. So let's have a look at this to illustrate these different graphs. All right, how they look like. I'm going to do it in R for you to understand. Just remember the formula as they are, and we are going to get that done in R. We will start by defining the P, and we are going to do all the graphs on only one. So P is a sequence of proportions starting from 0 to 1, virgule. Suppose I take 0.0301. Why do I do that? Is just because when I'm going to plot the Gini and cross entropy, because you want a smooth curve to appear, it's better to have more values within that range of 0 and 1. Otherwise, you would have um, a staggered shape. Okay. So here we go. We start. Maybe I will start by the deviance. All right. To start with, I'm going to start by the deviance. Why? Because the deviance is the one that will. Let me go here. Because the deviance normally, if you just look at it, it's the one that. Excuse me. The deviance is the one that will reach the highest value. All right. And then you will have a you will have the Genie index that will come down there, and then you will have the misclassification error rate. But the deviance is going to be the one with the highest value generally because of the log component that you are taking in there. So for this particular reason, I will start by it so that my scale is already predetermined, is already set, okay, so that the scale in R is already set to the maximum value, and then the rest will come inside. It will be okay. If I started by the others, which will be lower, the scale of R would have been default on the misclassification error rate, which is going to be lower than the deviance. And if it is lower, you will be having trouble to see the graph properly. Okay, so this is why I decide to start by the deviance. Okay, let's get back to the deviance. So we have our proportion set. We are going to compute the deviance. The deviance, as we note, is negative is a negative p times 1 minus p, sorry, p cap mk times log of p cap mk. So that's what we are going to do. Okay, we are going, don't forget that we have to do it for different classes. Okay, we have to do it for the different classes. So we are going to consider two different classes, which means that this is going to be, because when you are doing for p cap log of p, you have to understand that it does not end there. You have another class that is possible. Let's suppose k is equal to 2, for which you have to compute the same thing. All right, so it is going to be p. Let's suppose k is equal to 2. To make things simpler for us, we're going to take k as equal to 2. So it's going to be p cap m1 log of p cap m1 plus p cap m2 log of p cap m2, and p cap m1 is, let's suppose, 0.2 p cap m p cap let's suppose p cap m2 would be 1 minus 0.2, 0.8. So p cap m1 is 0.2, let's suppose. P cap m2 would be 1 minus 0.2, which is going to be 0.8. So we're going to have to express that in our formula here, which is going to be expressed by this. We have a minus here, and then we have p times log of p, which stands for one class, which stands for the second class. Okay, and then if you want, we can just plot these two together. Plot p. What we're gonna do here is, yes, we'll leave it as it is, but I'm going to set type equal to L, just for it not to be dots that gonna appear in the graph. Okay, I'll put it as L. Here we go. We get our first graph, as you can see here. Okay, we can increase the size of this graph as well, but this is related to the cross entropy or deviance. You see that the highest value is 0.7. It's not like the case of Genie Index where the highest value is supposed to be 0.25 as we seen before. Okay, let's continue. We're gonna now do the misclassification error rate. All right, sorry, misclassification error rate. And the misclassification error rate, as you have observed in the formula here, so let me just get there. You'll see that it is obtained by 1 subtracting the probability where you have the maximum, the probability within a class where you have the maximum, okay, the maximum km. But forget about the m here for the time being. It's just the purpose you are considering, irrespective of what region you are referring to. Just look at the km. The km is the maximum, um, the class which relates to the maximum. Okay, and how are we going to illustrate that in the R code? So let's get there. It's going to be illustrated by the code 1 minus p max between p and 1 minus p, which is the maximum between p and 1 minus p. If p is the maximum, because you will start by 0, do not forget that p in the horizontal axis starts by 0. So obviously p would not be the maximum. It would be 1 minus p that would be maximum. So then you would have a value that will relate to 1 minus uh, 1 minus, which one is going to be? So if p is equal to 0, you have 1 minus p, which is 1 minus 0, which is 1. So you have 1 minus 1. 1 minus 1 in the end would mean 0. So it will start from 0 here, right? And then this value will increase up to certain point to reach certain value. So this is what is happening here. You will see when the value is 0.1, the maximum would be 1 minus p would be 0.9. So the maximum would be 0.9. So it would be 1 minus 0.9, which is going to be 0.1. So when it is 0.1, it's going to be obviously 0.1 again, and it's going to go like this. So that's what we expect to have. Let's plot this through lines. Misclassification, just to differentiate them, I'm going to use a different line width to differentiate these. Okay, or we can leave it as the same line width, doesn't matter, because it's going to be relatively easy to differentiate this one. Okay, let's do lines of p miss. Here we go. You see that the maximum is going to be 0.5, but try to observe carefully what's going on here. When you say that the type is L and goes to 0.5, you see that this is the worst case scenario. When p is equal to 0.5, you reach the highest value, and you don't want a high value. You want your value to be here, or around here, to have a very good classification. Otherwise, it means that your classification would not be very good because your proportions are equally likely to occur. So the higher the value, obviously, the higher the deviance, the worse the situation, the worse the classification, the smaller the the higher the deviance, the worse the classification, the highest the misclassification error rate, the worse the classification, which is quite obvious and intuitive to understand. We have a last one to draw, which is the Genie index. For the Genie, we remember the formula, which states that you have to take p into 1 minus p for the first class plus the second. The same thing for the second class, all right? Remember that we are taking only two classes here for illustration purposes, okay? So the Genie it's supposed to be p into 1 minus p plus 1 minus p times p. All right, minus p times p is the Genie index. And we are going to plot the lines for the Genie index on the same graph, P, Genie. We are going to increase the line width a little bit bigger for us to see properly what's going on now, because we are going to be relatively close to the misclassification error rate. There we go. So this is the Genie index. All right, you've got the Genie index which you have here. The Gini index is computed as you see, and it goes close to the value here. So how do we get this value, for example, of 0, and how do we get this value of p? It's by taking into consideration the formula that you see there. Okay, and all the others. So, excuse me, when you get back to here, you will see that if you take p cap when it is 0.5, when the value of p cap is equal to 0.5, excuse me, there we go. When the value of p cap is equal to 0.5 here, this is p 0.5, you will see how we get this value here, which is how we get this value. What is this value? So let's get there. So p cap 0.5 multiplied by, of course, the reverse is 0.5 for the 1 minus p, 0.5. But this is for one class. We need to do it for the second class. It's 0.5 multiplied by 0.5 again, which means that you would have 0.25 plus 0.25, and here we get 0.5. So this is what you get as 0.5 here, all right? 0.5 is what you get here normally, and the other one is close to 0.7 or something. Okay, the smaller it is, the smaller the deviance, the better the classification. Obviously, smaller the deviance means the closer the p cap is to 0 or close to 1, the better the classification, irrespective of which measure we are referring to. But as you would observe here, is that this misclassification error rate has a limitation in terms that it is not amenable to numerical optimization. All right, let's get back to here. So I think that's a little bit what I had to discuss with you in terms of these impurity measures, that is the QMT that we were discussing earlier. Excuse me. The QMT that we were discussing earlier in the regression setting was the minimization of sum of squares, but here our aim is to minimize this error rate. This error rate, either one, the misclassification, you want to minimize it, or the Gini one, or the cross entropy, or the deviance, referred to as a deviance as well. You may wish to decide which one you want to minimize. Okay, normally I'm going to skip this. I'm going to skip this as well because we already discussed that. And what we are going to do the next time we meet is that we are going to apply the classification tree and the regression tree in R. The first example, we have to apply it with the ITER's data, and we're going to use another data as well to do classification in R. So that's a little bit all about decision tree. Remember what is the difference between the regression tree and the classification tree, and also bear in mind the similarities in terms of the procedure. Okay. Do not forget as well that we have to prune our decision tree. Remember that these measures that you are using here is what will guide you for cost complexity pruning, right? In the cost complexity pruning, we used a QMT here. This was a QMT that was used. That is, the impurity measure was the sum of squared errors. But in the context of classification tree, the quantity that is used here is not this. It's not the sum of squared errors, but it's going to be one of these three measures that I've mentioned here. Okay. In general, what we use is the misclassification rate. So that's all for today. Thank you for your attention. If ever you have any query, you are most welcome to ask me in the class next week when we meet for the explanation with regards to these different examples. Take care. See you.